The following is an exercise on maxima and minima. Pause the video at this point, have a go at the questions yourself, and then when you've tried them, you can restart the video and I'll go through the answers. Okay, let's have a look at question 1a. Find the stationary points for each of the following equations. Determine whether each is a maximum or minimum or point of inflection. In part A we have y equals 3x minus x squared plus 10. Now to solve this we start with the equation and then we differentiate it. So to find the differential, when we differentiate 3x we just get 3. When we differentiate x to the power 2 we get 2 times x to the power 1 or just 2x. And when we differentiate a number like 10 we just get 0. So dy by dx is equal to 3 minus 2x. Now to find a stationary point we want to find where the gradient is 0. So let dy by dx equals 0. In which case 3 minus 2x is equal to 0. Which means 2x is equal to 3 or x is equal to 1.5. But we have y is equal to 3x minus x squared plus 10. So if x is equal to 1.5, then y is equal to 3 times 1.5 minus 1.5 squared plus 10. Which means y is equal to 4.5 minus 2.25 plus 10, which is equal to 12.25. So there's a stationary point at 1.5, 12.25. Now we have dy by dx is equal to 3 minus 2x. So if we differentiate again, the second differential, d2y by dx squared, is equal to minus 2. The 3 differentiates to 0. Now if the second differential is negative, it means we have a maximum. So the stationary point at 1.5, 12.25 is a maximum. Now we can see this if we draw a graph. Let's have some graph paper, draw the graph of it, and we can see the highest point is 1.5, 12.25. Now in part 1b, we want to find the stationary points of y equals 2x cubed plus 3x squared minus 36x plus 30, and determine their nature. To solve this, we've got the original equation and we differentiate it. Now to differentiate 2x to the power 3, it becomes 3 times 2x to the power 2. 3x squared, or 3x to the power 2, becomes 2 times 3x to the power 1, or 3x. 36x differentiates to give 36, and 30 on its own differentiates to 0. So dy by dx equals 6x squared plus 6x minus 36. Now to find the stationary points we want where the gradient is 0, so let dy by dx equals 0, in which case 6x squared plus 6x minus 36 equals 0. Now we can divide all the way through by 6. So x squared plus x minus 6 equals 0. And we can factorise that. We want two numbers that add to make 1 and multiply to make minus 6. So that is x minus 2 and x plus 3 equals 0. Which means x is 2 or x is equal to minus 3. So we have stationary points at x is 2 or minus 3. And if x is 2, then y is equal to 2 times 2 cubed plus 3 times 2 squared minus 36 times 2 plus 30, which is 16 plus 12 minus 72 plus 30, so y is equal to minus 14. If x is equal to minus 3, we can substitute it into the equation. Y equals 2 times minus 3 cubed plus 3 times minus 3 squared minus 36 times minus 3 plus 30. So y is equal to minus 54 plus 27 plus 108 plus 30, so y is equal to 111. So we have two stationary points, one at 2, minus 14, and the other at minus 3, 111. Now, to determine their nature, we find the second differential. Now, d2y by dx squared is equal to the differential of 6x squared plus 6x minus 36. So that is d2y by dx squared is equal to 2 times 6x plus 6, which is 12x plus 6. Now if x is 2, d2y by dx squared is 12 times 2 plus 6, which is 30. And it's positive, so that means we've got a minimum. Now, if x is equal to minus 3, then d2y by dx squared is equal to 12 times minus 3 plus 6, which is equal to minus 36 plus 6, or minus 30. And negative means we've got a maximum. So we have a minimum at 2, minus 14, and a maximum at minus 3, 111. Now we can draw a graph of this. Let's draw some axes and then draw the curve. We see there's a maximum at minus 3, 111, and local minimum at 2, minus 14. In part C, we want to find the stationary points of the equation y equals 2x cubed minus 9x squared minus 24x plus 6. And we want to determine the nature of the stationary points. So we start with the equation and then we differentiate it. Now when we differentiate 2x cubed, we end up with 3 times 2x squared. When we differentiate minus 9x squared, we end up with minus 2 times 9x. And when we differentiate minus 24x, we just get minus 24. The number at the end, 6, differentiates to 0. So we're left with dy by dx is equal to 6x squared minus 18x minus 24. Now to find the stationary points, we let dy by dx equal 0. So 6x squared minus 18x minus 24 is equal to 0. Well, we can divide all the way through by 6, so x squared minus 3x minus 4 is 0. And we can factorise that. We want two numbers that multiply to make minus 4, add to make minus 3, and they are x minus 4, x plus 1. So x is equal to minus 1, or x is equal to 4. So if x is equal to minus 1, we can substitute that in the original equation. Y is equal to 2 times minus 1 cubed, minus 9 times minus 1 squared, minus 24 times minus 1, plus 6. Now that's minus 2 minus 9 plus 24 plus 6, which is equal to 19. So y is equal to 19. Now if x is 4, then y is equal to 2 times 4 cubed, minus 9 times 4 squared, minus 24 times 4, plus 6. So y is equal to 128 minus 144 minus 96 plus 6, which is minus 106. So we have two stationary points at minus 119 and 4 minus 106. Now we need to find the nature of the stationary points. So to do this we can differentiate again. Now dy by dx is equal to 6x squared minus 18x minus 24. So the second differential d2y by dx squared is equal to 2 times 6x minus 18 minus 0, or 12x minus 18. So if x is equal to 4, d2y by dx squared is 12 times 4 minus 18, which is 48 minus 18, or 30. Now positive means a minimum. If x is equal to minus 1, then d2y by dx squared is equal to 12 times minus 1 minus 18, which is minus 12 minus 18, or minus 30. Now negative means it's a maximum. So 4 minus 106 is a minimum, and minus 119 is a maximum. We can see this if we draw a graph. We can draw out some axes, draw the curve, and we do see that we've got a maximum at minus 119 and a minimum at 4 minus 106. Now in part D we want to find the stationary points for the equation y equals x cubed minus 3x squared plus 3x plus 12. Now to solve this we start with the original equation and then we differentiate it. To differentiate x cubed we have 3x squared. To differentiate minus 3x squared we have minus 2 times 3x. To differentiate 3x we just have 3, and when we differentiate a number, 12, we have 0. So dy by dx is equal to 3x squared minus 6x minus 3. And if we let dy by dx equal 0, then 3x squared minus 6x minus 3 is 0, and we can divide all the way through by 3. So x squared minus 2x minus 1 is 0, and that factorizes as x minus 1 squared is equal to 0. Now that means there is only one root, x equals 1. Now, if x is equal to 1, then y is equal to 1 cubed minus 3 times 1 squared plus 3 times 1 plus 12, which is 1 minus 3 plus 3 plus 12, or y is equal to 13. So there is one stationary point, and that's at 113. Now to find its nature, we can find the second differential. We have dy by dx is equal to 3x squared minus 6x minus 3. So d2y by dx squared is 2 times 3x minus 6, which is 6x minus 6. If x is 1, then d2y by dx squared is equal to 6 minus 6, which is 0. So that does not help us to know the nature of the stationary point. So we're going to have to do it by another method. So let's take a point on either side. Now if x is 0.9, then y is equal to 0.9 cubed minus 3 times 0.9 squared plus 3 times 0.9 plus 12. And that works out to be 12.999, which is very slightly less than our value 13. If x is 1, we know y is 13. And if x is slightly larger, if x is 1.01, then y is 1.01 cubed minus 3 times 1.01 squared plus 3 times 1.01 plus 12. And that works out to be 13.001, which is slightly larger than our original value. So we see it starts smaller than 13, but gets on the other side greater than 13, and so we have a point that's not a maximum or a minimum, it's a point of inflection. We can see this if we look at the graph. If we draw some axes and then draw the curve, we see the curve flattens off at 113, but it comes up from the left-hand side and then continues up on the right-hand side. So this is a point of inflection. Now let's have a look at a problem. A farmer has a length of wire 60 meters long. He has 2 posts and wants to use it to border a rectangular area along a wall, as in the diagram. So the wire stretches from the wall to one post, then to another post, and then back to the wall in the shape of a rectangle. If the distance of a post from the wall is x meters, find in terms of x the distance between the 2 posts. Now to solve this, let's label the diagram. Let the length AB be x. Then the length DC will also equal x, which means that BC is the rest of the wire, which is 60 minus 2x. So the distance between the posts is 60 minus 2x. Now in part 2, we want to find in terms of x the area of the fenced off region. Well, we can call the area y. Let y equal the area of the region. Then y is the width of the rectangle times the length of the rectangle. So y is equal to x times 60 minus 2x. So the area is x times 60 minus 2x square meters. Now in part 3, we want to find the maximum area the region can have and give the length and width of it. Now, y is equal to x into 60 minus 2x, and if we expand the brackets, y is equal to 60x minus 2x squared. So if we differentiate, dy by dx is equal to 60 minus 2 times 2x. In other words, dy by dx is 60 minus 4x. Now if we let dy by dx equal 0, then 60 minus 4x is equal to 0. So 60 is equal to 4x, or x is equal to 15. Now if we do the second differential, we have dy by dx is equal to 60 minus 4x, and so d2y by dx squared is 0 minus 4. Now that's negative, so it means we have a maximum. So we have a maximum when the width is 15, and the length is 60, take away 2 times x, which is 60 minus 30, or 30. So the length is 30 meters, and the area is 15 times 30, which means the area is 450 square meters. So that gives a maximum area when the distance of a post from the wall is 15 meters, the distance between the posts is 30 meters, and we get an area then of 450 square meters.